everyone, welcome back. You're ready for round two. So, again, if you have any questions, just interrupt me. It's fine. The plan for today is to finish finite MDPs, and the next lecture is going to be on some linear model. Let's see. I have to decide. Okay, so recap. We are in the online setting where we have some finite MDP with an unknown transition matrix P and a known reward function R and some initial state distribution. Finite. And we're interested in finding an algorithm that minimizes regret. Regret is defined as sum over episodes. So we're in the episodic setting. The agent chooses actions for h steps, and then the episode is reset.
Shouldn't H be a part of the MDP then?
Sure.
Okay.
If you want to. Yeah. And yeah, so regret is defined as the difference between the optimal value any policy can get in round K. So starting from a state as 0, sampled from the initial state distribution.
There's a question.
So the difference between that and the reward the agent collects. So VK is the sum over H equal 1 to capital H, reward of action A chosen at step H, and state SH in episode K. Okay. And now we looked at these optimistic algorithms, so we constructed a confidence set for the unknown P star. And the confidence set is CK delta. So this is a set of transition matrices that are not too far from a maximum likelihood estimate. So we want it for all as A. The one norm between this P in the set and our estimate denoted by PK. In the one norm is less than some function beta delta of the number of times we have seen the state action pair up to episode K. So NK of SA is sum over K prime is 1 to K minus 1. So we're not including the data from episode K, only before episode K. Now we're summing over all steps. And we count how many times we've seen this state.
So this is a time homogeneous model.
Yeah.
Okay. Yeah.
Okay. And then we also define this guy, like how many times we've seen this transition. And this estimate is just dividing the number of times we've seen this transition to a state as prime divided by the number of times we visited SA. Because you've seen these many times before.
Yeah. Do you want to say anything about the time homogeneous thing? Like, because some papers will do time inhomogeneous, time homogeneous.
So time homogeneous means that it's the same transition kernel in each time step of the episode, and we could relax that and use a different one, and we're actually going to do that a little later.
So the superscript in the indicator function should become primary.
Yep. And last time we spent some time proving what function we can choose, such that what we want is that the probability that the true model is in all the confidence sets is larger than 1 minus delta. And for that, we looked basically at that quantity, and we used Hoeffding's inequality to bound the difference with a couple of times union bound, and that gives you a number for this, and it's like something like this, square root s log n, so it's k with the number of stakes. This came from the union bound over this set plus minus, if you remember from the construction. That's log, and then there was something like SA divided by delta, and there's something that depends on this nk. So,
I think it's, yeah.
and then divided by, okay, let me just define it like this. Something like this.
There's an H against,
And so you, like, I used U as an argument here, because we're going to plug in the number of times we've seen.
Oh, okay, okay.
It's not necessarily 8.
Yeah, it was a pretty cool little trick that Trava did to get the U in there.
Yeah. Like, having the nk here is pretty useful for bounding the regret later. Because otherwise, if you just plug in maybe h or k times h, then this would be like a little larger, but the regret would be a lot larger.
And you also need to know what k is beforehand. Or no?
You do for this algorithm.
Yeah, for this. No, you don't need
Here
to
you
know.
don't.
Yeah, you could also have something that only depends on, say, h or the episode, and you don't have to have this count.
This is an anytime algorithm?
No, I guess you can't do this because the count definitely needs to appear here. Yeah.
Sorry, can you just restate what you meant there with by the end there?
Okay, so we want these to shrink with 1 over square root the number of times we've seen a state action pair, and that definitely depends on that number. Like, your confidence interval for some SA is going to depend on how much data you have there.
Right, but I mean, when we take that union bound,
Mm-hmm.
it doesn't mean, like, in order to choose the beta term there, don't we need to know k? Because that seemed to be the motivation of plugging that in there, at least from Trava's videos. Using the u times u plus 1
This
to split up
okay.
the probability of like the bad event
Sure.
across infinitely many things.
Yeah. But you could plug in like a counter. You just count the number of data points you have, and you plug in that counter here. That would also be fine, I think. But here you're taking sort of the union bound in a different order, if you want. Over time steps. That makes sense.
Okay.
That is just a minor difference. We anyways going to plug in k times h at the end. But it's nice to have it a little bit tighter. Okay.
Oh, okay. Yeah.
And this business of proving confidence bounds is quite important. It appears all the time. So sometimes, you have a suboptimal bound, and it's because you don't have a tight bound for this, or your estimator is not good, or you're not having a norm that behaves nicely with what you want to bound. And then maybe you have to prove a new confidence set. So this appears quite a lot. And also the construction we used is pretty common. Most proofs were like this.
If you chose the 2 norm instead of the 1 norm, do you know what that might do to the regret?
Yeah, I mean, I can bound the 2 norm in terms of the 1 norm.
Oh, yeah.
But Yeah, I guess if you use the 2 norm, then it's more like linear model, and you could use linear least squares estimated probably. I'm not sure if that would be the same. No, I don't know. You can do this. Yeah.
Yeah, I guess it's a linear model. You pay SA, just like you pay D.
Yeah.
Oh, and I guess SA doesn't pop up here because D would pop up out of the square root.
Yeah,
You
yeah.
can get S in the square root. Yeah.
You can play with these and see if it gets you something better. I don't know for this case.
No, it's
I would think like the 1 norm is a good choice because these are distributions.
No, I was just curious. Like, if you put a 2 norm and then you could almost treat it as a linear model. D is going to appear out of the square root. D here is SA, or even or even SAS prime, and then now that appears as a linear term instead of a root. Okay.
Okay. So are there any questions on the confidence set or the proof? So then we have this algorithm called UCRL, which is defined as follows. We first compute this confidence set k delta for some fixed delta, say. So what we're aiming for is a bounded holds with high probability, and then choose the optimistic policy, pi k's, argmax. Our policies then maximum over the models that are still in the confidence set. And then we pi the value of the policy under this model for the given starting state. Yeah. And computing this, I think is hard. I'm not aware of a particular hardness result, but it seems difficult because it's like a non-convex function. Because we're having the maximums in here from the Bellman equations.
I think it's a QP.
Is it?
Yeah.
What's a
I'm-
QP?
A quadratic program.
I'm not convinced that that is true.
I think you could. Okay. Maybe I think you can relax this as a QP, but that doesn't make it like easier. Like maybe for a price of D, you can solve this.
Yeah.
Or as a QP.
What we're going to do later is relax this, and then you can solve it. Actually getting the same bound. But yeah, as written, this might not be that easy to compute.
Yeah, I think it's just like you have to search over the whole. You have to search every P to find the R times.
Okay. So what we're going to show is that the regret of this algorithm with probability at least 1 minus 3 delta is at most something like okay, we're going to see, but I think it's case like h squared s square root a k, and then there's logarithmic factors that I'm not writing right now. Oh, and the log 1 over. Well, if I'm not writing it, it's still correct. We're interested in the dependence.
And on the relevant quantities. Yeah.
Or the relevant quantities. Right. Okay. So you proved a little bit tedious. Will we get through it? So somehow, okay. It's an optimistic policy, so somehow we want to use this. And the reason for choosing an optimistic policy is that we can relate it to the optimal policy somehow. Because we don't know what the optimal policy is, so it's always difficult to argue directly about, I don't know, what the optimal policy is going to do for some model P. Okay, let me introduce some notation. So P K is the optimistic model. insert k. So the k dependence comes from the initial state. And we assume the event epsilon, which is y, which is just this intersection of the confidence sets. So assuming these are true, so we're going to pay like.
So we're assuming that epsilon's equal to the intersection, or assuming that the true model lies in the intersection is the event.
This true. So that this event is true for what follows.
Oh,
If
okay,
it's
okay.
not true, then this happens only with probability delta, and there's going to be some union bonding. That's
So
why
we're just
this-
assuming that this is equal to this. All right.
Mhm. So this is a definition.
Yeah.
So we condition on this.
Yeah.
Maybe that's better. Condition. And now we decompose the regret into 3 terms. Okay, the instantaneous regret. So this term, right? So first we introduce the optimistic model. The optimal value under the optimistic value, under the optimistic model. Now I've subtracted that, so I'm adding it back in. And then I'm comparing the optimal policy on the optimistic. Then I'm comparing the optimistic model to the actual model. So this is the same as the value of the policy that you're choosing. The value of our policy under the true model. And then adding that back in. And we're going to bound these terms one by one. So far so good.
Huh?
So far so good.
Well, can you just tell me, when you wrote that theorem, was probability, like what is that? Is that 1 minus?
3 delta.
Oh, 3 delta.
Oh, okay. I guess once I introduced a
Okay.
notation, it doesn't really matter.
I see.
But well, if you introduce a constants, then yeah, this comes from like a union bond over 3 events
Yeah,
that
I see
appear in
that.
the proof.
Okay, I thought those were 2 that looks like delta times delta.
Oh,
When I
okay.
first read it, I was very confused.
Yeah, yeah. Indeed.
But I see now.
You can also replace delta by delta divided by 3, and then
Yeah.
you can state it for this.
Yeah.
Right. So the first term. So the first term is where we're going to use the assumption that we play an optimistic policy. And the fact that the true model is in the confidence set. By that we know that this difference is going to be less than 0. By choice of pi k, and the fact that p star is in ck. Okay, and that's what I meant, like using the optimistic policy makes it easy to reason about the only term where we use the optimal policy. All the other terms are about the policy that we played. These are sort of more on policy if you want. on this term and then the second term. Defining the third term as xi, then by definition of the value function, the expectation of vk is going to be the same as this, even if you condition on the previous data. Let's say vk conditioned on that is the previous data, fk is previous data, and the starting state. This is v. Taking the expectation of this term, we get 0. So if we want to prove a bounding expectation, then we just take the expectation over everything, then we would be done already.
Oh, wait, so do 2?
Hmm?
So do 2, like bound.
Well, not with 2, but with that term.
Oh, yeah.
Now for a high probability bound, we need to use something like Hoeffding's inequality. So we know that psi k is bounded by age. Right, so assuming the reward is in theory 1. The only issue is that this is not an IID sequence, right? For example, we've changed the policy, so it's definitely not the same distribution.
I'm confused about what does it mean to condition on the previous data?
It's the expectation over the conditional distribution, right? So you fix a particular event like this, and then this is just a distribution conditioned on that this is true.
I mean, what's the difference between, so if we don't condition on the previous data, is it still 0, the expected?
It is still 0, yeah. But I'm going to use this property, that's why I wrote it like this. So the property we are going to use is that psi k is a martingale difference sequence. And a martingale difference sequence is exactly defined like this, so the zero mean property, conditioned on a filtration. So this is called a filtration in this context. So you can think of this as like a random walk. So you have steps indexed by k, and you draw some random variable with a 0 mean, and then you go up or down. But conditioned on the outcome, you're again going to draw a 0 mean random variable. And if you sum them up, you have some sort of a random walk. And these random walks with this property, they behave almost like IID sequences. So, summarize this. Psi k is not IID, but a martingale difference sequence. And there's like the extension of Hoeffding's inequality to that setting is called Atsuma-Hoeffding's. And it says that 1, if you average these random variables, then the sum or the average is smaller than the range times square root of 1 over delta divided by 2k with log probability. Right, so that implies that 3 is less than square root h times square root k of 1 over delta divided by 2k.
Just to clarify, those two conditions you there are the only two things that need to hold for it to be a martingale difference sequence. That's the definition, in case you're wondering.
It's just this, and this is like a boundedness property that is used in.
I was just saying, like, if you were curious on what a martingale difference sequence is, it's just any thing with like
It's
a random
like
variable with these two properties.
Any sequence of random variables with this property.
Yeah. It doesn't also need to be bound, like it needs to be finite. Like the magnitude of the random variable itself needs to be finite. Do you think it's
Not
infinity?
necessarily.
It can be infinity?
Yeah.
Oh, I thought it had to be.
I mean, okay. It doesn't need to be in some range, right? But if it was infinity, then with constant probability, then yeah, the expectation would be infinity.
Yeah.
Yeah.
That's
You need
what
the
I-
expectation to be well defined.
Yeah, yeah, yeah.
Okay.
And maybe it would be useful to mention why this is like our first time using this non-IAD stuff in planning. It was always IAD, I guess. And maybe you can say a couple things of what happened here different in the online RL setting.
Yeah. So this is pretty common in any online algorithm because you're creating this data, so you have these dependencies in your data. And then if you look at the right quantities, for example, this, then you have the zero mean properties, and yeah, you just want to bound the sums. And yeah, many results extend to the setting. And that's like, okay. If you have like a sequence of random variables x, x1, x2, 3, and so on, and there's like, okay, the filtration that corresponds to this is just the outcomes up to some time. Let's say k is this, and then we say if the expectation of xt plus 1, conditioned on that you know all the realization of the random variables that come before that. So conditioned on on ft. If this gives you an expectation xt, then this is called a martingale. Right, and this conditioning, it comes from, is used because here we collected some data and we condition on this data, and then we want to see how, for example, some quantity behaves with respect to this conditioning. So this is a martingale. If you have an inequality like this, then it's a super martingale, and like this it's called a sub-martingale. So if you think of just the super martingales, then you know that in expectation your sequence is not increasing in a sense. Right? It doesn't mean that the realization, you can still go up a little, but in expectation you're going down. So you can create upper bounds of that.
And I guess the difference between this and the planning setting is in the planning setting, you know P and R, so the only data you're getting is about maybe the Q values you're trying to estimate. And you can treat that as a random variable. You started a given state action pair. Once you're done interacting, what you do at the next step isn't conditioned on what you did at the previous step. You just keep rolling things out. In this setting, you can imagine that there's an optimal sequence of data you can observe such that you learn that you can shrink your confidence sets as quickly as possible. But you may not see that data. So what you do at the current time step is very much conditioned on what you did at the previous time step. So you can imagine different rollouts, seeing different random variables. Your confidence sets will behave differently. And so that's where we get all this non-IAD stuff. But I guess Johannes is saying is right, like even in like a worst case flavor, you can keep going up, but like you can only go up so much with some high probability before you go back down again. So you condition with some probability that, you know, for that random walk to go to infinity is almost zero. So the question is like, how high can that random walk go before it has to go back down again? I think, does that make, so did that help with you guys? Why it's different between this and the planning setting?
So even in like, okay, in the planning setting, I guess you had these fixed designs, so you would just sample always from the same distribution. But even in the planning setting, you could consider an algorithm that adapts based on your data.
Yeah.
And then you would also have non-IAD data.
I don't think that, you guys didn't do that. I don't think we did that.
No.
We just treated everything as like a estimate Q by doing rollouts.
Mm-hmm.
in martingales and you want to stay in the field, yeah, I recommend to look into this a little at least. Yeah, so if you have a martingale and you take, you define a new sequence as the difference between this and that. So you can, yt I could define this as xt minus the expectation of xt condition on iteration. Then this is going to be a martingale difference sequence, what we had here.
Actually, the inspiration for a lot of this math came from gambling. Casinos wanted to know, like, realistically for every gambler, like how long could a gambler like keep increasing their winnings before they would eventually have to go back down? And they wanted a different sequence. I think where the expectation was positive was in favor of the casino and negative was in favor of the gambler. So they wanted to design sequences where the expectation would converge not to zero, but something a little above, to guarantee that they would always asymptotically.
Yeah.
So that's why you have these.
Yeah, martingales are also used a lot in finance. Okay, so that means we are done with the third term. Yeah, it's all written up in the notes. You can also
There's a
read.
typo. The algebra opting from there, and there should be no k in the denominator.
Here.
The one below. Yeah.
Yeah. Yeah, thank you. This is some other things. Okay, and now comes the last term, which is the longest to bound. Are you okay with me erasing that part? You memorize the confidence set. I think I'm trying to keep this part and this part, and maybe use left and right side. And now, so maybe you have seen the lecture of Java from last year, and the third part I think has a small bug. Maybe you've seen it, maybe you haven't, which I found out yesterday at 8. But it's minor and it can be fixed. Okay. So, okay, we're looking at these value functions. So what we're going to do is first use Bellman equation to sort of unroll this, and then use the confidence set to reason about the difference between p tilde and p star. And somehow we want to use that, yeah, these two are close. They're like in one norm, they're close, right, by the definition of the confidence set. And yeah, you can already see, like, the closer they are, if they were the same, then this term would be 0. If they are small, then hopefully the sum over these over k is also going to be small. That's what we need to show. So we have Bellman's equation.
I guess we've already seen this in the Batch-RL setting sort of as well. Like in the Batch-RL setting, we also showed the similar result between like a misspecified model.
Yeah, I didn't check exactly what we did.
Yeah, I just remember Shava mentioning this in the lecture as well, but I think he mentioned there's something different here. Slightly different.
For sure, I think, yeah. So this is sort of the crucial step for getting this required bound, where we use how efficient the confidence set is. So, yeah, I think it's good to go through this.
Oh yeah.
So if I look at the value of some policy pi at state h, I can write it as the reward plus the transition probabilities under the policy, and then the value function vector at h h1, h plus 1. Okay. So now we're going to look at these value differences. Of the policy pi k, so just what appears there. Under, I think there was the first typo here. Oh. Yes, the optimistic model. SHK minus the value under the same policy under the true model. And now we unroll this for one step. So the reward vector is just going to cancel because the policies are the same. So we get m pi k. Okay, there's so many indices. Tilde is k. So far, we need the value function. So b h plus 1 I guess we can't take out the value function because 1 depends on p and p tilde and 1 on p star. Would you agree? M pi k p tilde h plus 1 pi k p tilde minus m k p star h plus 1 p star. Okay. And now, and now we want to create a term that we can control, so something like p tilde minus p star, but because these vectors are different, we can't quite get that. But we can add and subtract m pi k p star v h plus 1 pi tilde pi k. So now I can, now this vector and this vector is the same, so I can group m pi k p tilde minus p star vh plus 1 pi k p tilde, which is looking promising because we know how to control this. And now I have one more term, pi k p star, and now the p star is the same, so you can do that. point, I think those two were swapped. But we needed in this order to bound this term. Like, it's like that is very minor. Okay, so now we can finally use what we know about these two guys. So taking the one norm on this, okay, this is like an inner product, and we know by Cauchy-Schwarz that, or held as an inequality, that the inner product between A and B is less than A1, the one norm of A times the infinity norm of B. Okay, so we apply this to this term, which gives us P tilde minus P star in one norm times the infinity norm of this value function. Okay. And let me just, there's something else here which we can do. At first, this we know is less than 2 beta, because we know if we do the triangle inequality and relax it at pk, then then this difference is at most beta, so we get 2 beta delta. Okay, so where are we going to get the states from? We have certainly can have the state as k, and the action okay, this is at most h, and that's for something here. Okay, so right now I'm wondering where the a came from. I guess this is okay.
Shouldn't that be the policy, pi k's action, something like that?
Mhm.
Because it's the same policy for both.
This came in where? Well, sure, for sure it's the policy section. Okay, from here. Yeah.
Something like that.
Yeah. Oh yeah,
Those-
because this is going to select like
Yeah.
a row or column of this matrix.
Oh, yeah, for a given S.
Yeah.
I guess otherwise it takes a transition matrix.
Yeah.
But where does the 2 beta come from? Sorry.
Okay,
The two.
let's do this explicitly. P tilde, so I'm looking at this term, I introduced our reference model, the maximum likelihood model. Star, one norm, and then triangle inequality. And now we know P star is in a confidence set, so this is at most beta. And we know the optimistic model is in a confidence set, so this is also beta, so we get the 2. Oh, that was fast.
Wait, what's the difference of P tilde and P just R maximum likelihood? Aren't they the same thing?
P tilde is the optimistic model. So P is the maximum of a models in a confidence set, where we maximize over the value, the optimal value function. And PK was what we estimated using the counts.
Oh, fine, yeah. I realize.
And the confidence set is defined with respect to the PK, not the P tilde K. Okay, and so this is 2P.
Sorry, what happened to the m pi k in the last?
Yeah, I think that the M pi K gives you the A, the action that
That's
was
not there in
selected.
the previous step, right? The second last one.
Here?
Yeah.
Yeah, okay, I guess. here, and the state also goes here, this state. So I just, I have no space to add this in.
I guess pi k was greedy or deterministic or something.
Pi k is the
Oh.
optimistic policy, but it gives
yeah,
us
that's
this
fine.
state. Yeah. So now we need to deal with this term. So the value function at step h plus 1 is just the expectation over the states that we're getting. And this difference, the expectation of this difference is the same as this one step later. So this is delta h plus 1 of k plus the expectation of delta. Now again, here we need to condition on the previous data up to step h. Minus delta. So this I'm just adding and subtracting because we want the recursion. And the expectation, like these two terms are the same by definition of the value function.
Is that delta k plus 1?
No, h plus 1, and we're in the same episode.
Oh yeah. Oh yeah.
Okay. And then this, again, okay, this by definition is another martingale difference sequence. It's, we call eta k h plus 1. And now finally we have the recursion that we are looking for. So we know that the second term in our graph, this is just delta 0 of k. So now we can use this inequality and we get delta h, and then we use it again and again and again until the end of the episode. So this is less than sum over h equals 0 to h minus 1, 2 beta delta of nk s h of k a h of k times h. And now we're getting this martingale difference sequence h plus 1. Yeah, why not? Right, maybe we can split those terms. So eta 1k plus eta up to h. Okay. So martingale difference sequence, we can use the same as before to bound this by, yeah, we need to argue about the range, which can be as large as h, because here we have value functions. So that would be less than yeah, maybe we want to sum this up over k as well. And then we get this is less than square root h k log 1 over delta divided by 2. and the range. Okay, so what happened here? Yeah, it's again like what we did over there. Like we're summing up this martingale difference sequence, we argue about the range, and then use Satsuma things. So these terms are essentially just noise in a sense.
So the only difference being an extra factor of h.
Yeah.
Oh, because you're summing over h as well. Right.
Well, we're summing over h and k, and each of those guys, now the range can be h.
No, yeah, I just wanted to know where the extra factor of h came, and then I remembered in this one we're not summing over. So this one we're summing over t, this one we're summing over k.
Yeah. Okay, and now we're finally at a term which relates the width of the confidence set to the regret. So here you see if you choose beta too large, then our regret is going to blow up. And okay, time. Okay. Now you need to remember the definition of the beta delta, which is something like there are some logarithmic factors that depend on delta and other logarithmic quantities, and actually s. And then there's divided by square root nk of s, h of k, ah of k. Okay. And this is, I think, where the other problem is in the notes from last year. We'll see. But in general, like, okay, when you're summing up these confidence width of something like 1 over square root number of counts, then this is like summing up 1 over square root I from I equals 1 to some number n. And this is less than 2 square root n. So how can we see this? Well, okay, one trick is to integrate this. Okay. Can you see this actually? Okay. So this is my k-axis. I'm going to draw like a bar diagram where this is the height here is 1 over square root k. Right. Like this. And we want to sum up the area. Now you can draw the continuous curve, which is defined as f of x equals 1 over square root x. And you see that the bars are below this, right?
Don't you need to shift it a little bit or something like that as well? I remember.
Like at the 1, this is going to be 1 over square root 1, 1 over square root 2, and so on. Right?
That's right.
And now, okay, I can't integrate from 0 because then I guess doesn't. Is it converge? Maybe converges.
I remember having to shift this when I thought about it for some reason, but.
I mean, wouldn't you start at 1 anyways?
Well, I want to include the first
Start
one.
out by 1. Like x minus 1.
And it does converge, so it's no problem. Okay, so this goes to infinity. We can just integrate from 0. Why not? So then you need then you need to reason about why the integral converges. You could also start at 1 and then add the box that we are not integrating over. But okay. By this picture proof, we know that sum over I equals 1 to n 1 over square root I is less than integral from 0 to n 1 over square root x dx.
Yeah, you have to add, I think you have to add the function at a specific, like it's the sum is less than the integral plus like f of 1 of the, like I think of the left, f of 1. Okay, so like but your sum starts at 1 here.
Yeah, the sum starts with 1, so I draw like this.
Yeah, I think the the inequality is the integral from 1 to
Yeah.
infinity plus f of 1. So you just have to add the initial value.
Well,
At least I remember from the,
it's not generic. You need to check that what you're summing over is below your function. Right? And if the integral over that function converges, then you're fine. And this works here. So this is square root 2 square root n as promised. And here you don't need to add anything. But sometimes, okay, maybe you could also start with 1 and then do this block separately.
Chava didn't do this last year, did he?
No, I think he used like a telescoping argument.
Okay, because I remember commenting something to do something like this, but then he did some other argument, and I was very impressed that you could do it a different way.
So I think this is a useful trick to see quickly if some converges. It also appears quite often. And Java's proof was like 1 over square root I is less than 2 square root I minus 2 square root I minus 1. Which is, yeah, like a similar thing. Okay, so how do you prove this? Oh, I would again go to the continuous setting. Okay, if you define f of x as 2 square root x, then this is a concave function, right? It looks like this. If you fix some x, x equal a, then we know because it's concave that it's below the linear approximation at point A, so we know that f of a is less than, sorry, f of a plus x. This is less than f of a plus x times the derivative in a, and you compute this, and you get this sort of inequality.
Can't you also just use a telescoping argument with this one?
Well, this is the telescoping one, and then you sum this up, and then you get the same.
no, the integral is right. It's n minus 1. So it'd be, you'd start at 0 and then you get an upper bound.
You start at 0 and you go into n.
Yeah.
And you want n of these boxes.
But I think that's an upper bound on this sum.
It's an upper bound in the sum,
Yeah, okay. There was an inequality there.
Oh, there's an equality. Oh, yeah.
Okay.
Good catch, yeah. It's not the same, yeah, obviously. So yeah, when you see this, you hope that you get something like square root nk. And then working out the details takes a little bit more work.
If anyone's wondering how people generally figure these things out, graphs, at least. Tell me in comment.
Yeah. So should we go through this calculation? I think it's going to take the remaining part.
Did you have something else in mind after?
Yeah, I had like the UCBBI, so the computational efficient version of this essentially, which could be interesting as well.
Maybe we can do that as well. Doesn't Chava go over the details of this too?
Oh, this? Yeah, so yeah, but there's like a small problem. It's fixed in a lecture note, I heard. So he was doing something like, okay, when you sum this up over k and h, and you condition over some pair A as S and A, then, okay, so we had the indicator that the state S KH is S and the action H K is A. No, divided by NK of SA. Okay. And then, okay, okay, we can do the sum over h because this doesn't depend on h. So if we just define the sum over this indicator in one specific episode k as mk, then we get the mk here. So this is number of times we see SA in episode k, and nk is m1 of SA plus mk minus 1, because our estimator only uses data up to k minus 1. And this is what Java was missing, I think. And you have mk here, and you only have the sum over the mk's to k minus 1. And then you need to work a little bit more. Okay. But I think you can look this up in the lecture notes and let me know if you find further typos or like problems. So let's spend just 10 minutes on something else maybe, unless there's like urgent questions you have now on this. Alright, maybe we should conclude though. Yeah, so once you bound this sum here, there you get your O of h squared as ka. And this is sort of the leading term that gives this regret bound. But I don't want to that. Okay.
So why are we like summing over k to h in the beta?
Here?
Yeah.
Yeah, okay, so
You went off k.
Yeah,
You
yeah.
went off h.
So here we had it for a specific k. Yeah, okay, if I'm having the sum of these, then it's just over k at the end when we are bounding. Okay, we need to sum these up over k, right? That's where the sum comes from, over k. So when we bound the regret, we need to sum up all these terms over k, and that's what I did here just to see the final result. And same thing here, so this bound is for when you sum over k as well. Yeah, it's a bit long, so hard to fit in one lecture. But I hope you see some of the ideas. Like, okay, so the main ideas were some terms behave like noise, and you have these martingale difference sequences which help you bound these terms. Okay, and then somehow you need to use that your p tilde model is close to the p star model, and that, if you do it correctly, gives you this width of the confidence set, which is the beta. In that case, like 1 over square root I roughly, and 1 over square root I is then gives you the square root k because you have k terms. And in fact, you're summing over all the SA and some h, so that's where you're getting additional terms from. Yeah, but that is sort of the generic proof strategy for almost all proofs that use optimistic algorithms. And that's not the easiest one to start with. Like if we were discussing bandits, this would be much easier and the same style of proof. Okay. Yeah.
If you want to do questions.
Yeah, maybe
we've got,
let's do
like,
questions.
7 minutes.
Yeah. Let's do questions first.
Okay, yeah, this is so we have 3 questions on it. Someone has a question, but I don't think he's here, so I shall ask it for him. From my understanding of the optimism principle, the agent constructs probable models and uses the highest reward one for planning. Does the optimism principle always have to rely on an environment model? Are there other exploration strategies for more complex settings when the model is not available and we don't want to plan? For example, due to resource constraints.
Yeah. And I guess no planning is difficult in MDPs. Some sort of planning you need to do.
How about the model-free stuff?
But model-free, okay. Okay, of course you can have like policy optimization, something like this. But okay, So the optimism, you can also use it for value functions, for example. So this is UCBVI, which we don't have time to discuss right now. But yeah, instead of estimating first a model and then compute the optimistic policy, we can just directly estimate the value function and construct an upper confidence bound on the value function. And yeah, there's like a simple form where you can compute the optimistic value functions using backwards induction or like value iteration. And this is the idea of UCBVI. So we can discuss that briefly next time.
You know, but then I'm just trying to relate that to there's that Q-learning paper as well by Chi-Jin, which he claims in the paper is model free, but UCBVI is still model based. And do you know the difference exactly there? Because I haven't looked that much.
No, I would say optimistic Q-learning and optimistic value iteration is almost the same, but maybe I'm wrong. Yeah.
So the claim in the paper
Because
as well
it depends on how it depends on what you're estimating. So in UCBVI, they're learning explicit models of the reward and the transition kernels. And then they're using,
Not really.
they learn in UCBVI.
Oh yeah, okay.
They're learning PK, RK, and then their bonuses for the value functions are based on the Bernstein bounds of the respective, like some use of the kernels and the rewards. They do it very intelligently. In LSVI UCB, there is no use of the model. There's no use. You don't estimate. Okay, so you technically estimate R, but not really. You're just estimating the expectation of R plus P transpose V, because you know P transpose V. The expected value of this thing is V of S prime, which is in this case equivalent to the max Q value. So you're doing value iteration in the sense of you're just using your Q values to estimate this P transpose V term, which we're learning explicitly here.
Right.
So the model.
So UCBVI uses an estimate of the model for the backwards induction.
Yes.
Okay.
Yeah.
And if we can replace that with samples, it would be model free.
Yes.
And
Depending on how you define
Q-learning.
model free.
yeah.
Because then we technically, I think VTR, we haven't decided if model free or not. But like there's like, Java does not like this distinction, and I'm kind of seeing why.
Yeah.
Or the other difference, I guess, is that in UCBVI, their space complexity is higher than the Q-learning version. As in, it has an S squared dependence, while the Q-learning one just has an S dependence.
Yeah.
And I guess it's because they don't store the transition model explicitly.
Yeah. So if you do like this least squares valued
Yeah.
estimation. Yeah.
But then I think, if you actually compare UCBVI, Chi-Jin has the Q-learning paper. I think it's some factor of H or S suboptimal. I think it's H.
Yeah, it's a squared H off the lower
That's
bound.
huge. That's like, I mean, if you care, if you have 1,000, if your horizon is anything interesting, like 500.
Yeah, it's square root of
Right.
H cubed instead of square root of H squared.
So you pay, and okay, you can either store the model and pay in memory, or you can not store the model and pay in samples.
Yeah, but he doesn't know if that's tight.
Yeah.
Like, is there a lower bound for the?
There's a lower bound for the problem setting, but not for Q-learning.
Yeah. Okay. Next question.
Okay, my question is that a little bit confusing about manipulation of doing the kind of inhomogeneous relaxation of the confidence set in the UCBVI. So can you explain more about that?
Okay. Yeah, I haven't presented yet, but I guess the relaxation is for doing the backwards induction, so you can compute the optimistic policy efficiently. Yeah. So maybe let's go over that next time quickly.
Okay.
That's okay.
And then there's a question from Matthew, who's on the Meet call, which I don't know if you want to ask it.
Oh, sure, definitely. Sorry, I just had to switch my headphones quickly. My question is more just generally about online reinforcement learning. Are there any settings where it might be able to vary the initial state distribution? Of course, assuming we're able to do so over the different episodes, maybe for improving accuracy or optimizing confidence interval length or anything towards that.
What's the question? I didn't get the first one.
As a-
Varying the initial state distribution
Yeah.
is useful, basically.
Well, if you can choose that. Okay, I guess you could construct an equivalent MDP where in the first step you pick the initial state. add like one special state as star or something, and like as actions that go to all of the initial states. And you add this to your MDP, and then you get to choose the initial state. And, yeah. But also, okay, it depends on what you want to achieve. Because here, when we defined the regret, we were conditioning on the state that we observe. So it doesn't matter which state you get, kind of. Right? But if you want to maybe say have a pack result over all initial states, then it could be useful to select the initial state. Just yeah. But you could
Yeah, because I don't think there's any regret bounds that are like conditioned on the, because like you can imagine you're at the goal state, but that for whatever reason doesn't really change the type of bounds.
It definitely changes the pack ones, right? Like the pack ones usually hold for some initial state or initial state distribution or something.
Right. So if there's a distribution shift, then maybe you want to select the initial state if you can.
So why do regret ones not care about this? And now
Wait, okay. I think we changed the lower bound if you could choose the initial, because the initial state distribution is conditioned on you building a tree and then finding something. But like if you could start, if you had the option to start from any state, then it should just depend. Well, I guess it would still be, you'd still have that S because you have to search through all the initial states.
Right.
I guess the one thing I do remember is that at least in the Q-learning paper, it was clearly explicitly stated that the initial state was adversarially chosen, and that was the result it held for that setting.
Yeah.
So are these are the results like
Which Q-learning
assuming that-
paper?
Which is the same here, right?
Yeah.
If this is adversarially chosen, it would still everything.
Yeah,
is
yeah.
right.
But if it's not adversarially chosen and you know it, then it seems like we could do better.
Yeah, that's a good point. Maybe.
Maybe, but then like you could still build a tree where you would have to like, you could choose the initial state you start from, which is like the best thing. Well, okay, unless the initial state distribution is just the goal state, but even then, I think like the most realistic assumption is you can choose the initial state. You still have to choose as many states, and you can hide the reward in whatever the last state. Needle in the haystack problem.
Right.
You can still,
So- Yeah, problem seems to be that the baseline depends on the state, and now you're selecting the baseline also. So you could pick a state where the baseline is not good, or where the baseline is trivial.
yeah, because you could imagine if you can choose the initial state, the optimal, and then the reward there is 1. The baseline is now H, assuming the dynamics hold.
And for pack results, we wanted to just be close to the true value function for the initial state.
Yeah, or some
Policy
distribution.
or something.
Yeah, I guess if you wanted that to help, you'd also have to come up for you'd have to think of a metric and where that would help. Like I guess that's like it wouldn't help in regret, for instance, too much. If you could choose or vary the initial state. Or I guess the best case being you can choose the initial state like that. So I don't know how much, like at least in the regret definition, I don't know how much that would help. But for a pack type result, it definitely could, because it would just your pack result is easy. You just start at every state. You just start at a different state, collect information about that state. But I mean, the pack result is still SA, so I don't know how starting at a state would help too much. You'd still get problems.
You can always think of the bandit setting. Like a lot of questions are not specific to MDPs and planning, so just remove the planning and it always gets easier. So if you have a contextual setting, so H equal 1. And the states are your context. And now you want to perform well meaning, okay. You presented the context, you say like an action, you get the reward, episode ends, okay? And you repeat that. And you want to be good on all possible contexts. Now if you can select the context, you could specifically select context where you still need data, say. And then if you want to guarantee like a pack result for all the contexts, then yeah, it makes sense to pick the context by hand.
If you want a guaranteed overall context. But is that necessary in the pack results, or is it just like sometimes stated over only the initial state that you're good or something?
Yeah, if it's, well, even if it's stated for one specific context and you can select that context, it's of course easier than if the context is sampled from some distribution, then
Yeah.
you see the context you're interested in.
Yeah.
Oh yeah, because then you can just choose the context with 0 reward. You
Yeah.
know it's 0 there, you're done. Like you don't. That's it. You're right at that context. Or the value function. You pick the context with the lowest value function, and then you write there. That's the easiest thing.
So yeah, some interesting questions there, like regarding your design, how you can use the context distribution, or how you should use it if you can influence that or not. Maybe more in the linear setting, when you have correlations. Otherwise, it's like, okay, you can learn about that state, only appear in that state.
Yeah, the linear one seems very useful.
But yeah, for the tabular state, it'd be a weird result because then would the baseline be the context you picked? You just pick the context with the lowest reward because it's the easiest thing to learn about, and then you've just found a good policy for the worst state.
Yeah.
Maybe that's like what the algorithm is. But yeah, for the linear setting, it'd be interesting.
But I mean, clearly in the pack setting, if you want to guarantee good results over all states, it would be
That's not
far
pack
more
setting.
ideal. Like,
Pack setting is for the initial state distribution, which if you can pick, you just pick your initial state to always be the state that's easiest to like learn the good policy from,
what needs to hold over the initial state distribution?
which is
Or
which you're
uniformly
picking.
over all states.
Oh, if you can pick it,
Yeah, that's the exciting one.
but if you,
That's like would that actually help? If you could pick the initial state, which is the nicest,
yeah,
which is
and you're comparing to some initials to that initial state you picked,
Yeah.
that seems very odd. It should be like compared to what the initial state that someone else picks.
Yeah.
but that'd be an adversarial result, which is what already.
Yeah.
So the question is like, and then that was a good question is, if you vary the initial state, would that help? And then you think of the nicest setting is you pick the initial state, the one that benefits you the most. And then would that just be the one that's easiest to learn about?
I don't know if that answered the question. Lots of discussion.
But for the linear setting, it makes sense, because then you could almost pick the initial state distribution with maybe the best generalization. Like where most